Hey guys, welcome back. Chapter 9 is called Multiparticle Systems in the textbook. In looking over it, I decided that really what this chapter is about is getting more realistic about real systems. So I call it getting more real. Basically, real systems have lots of little pieces, and they all you have to take into account all the parts of the system together to figure out what's going on. And so it's complicated. I have drawn here, or have diagrams here of a couple of example systems from the text. In one case, we've got multiple objects that are sort of spinning and whizzing around. In another case, we've got a couple of blocks connected by a spring. But obviously, this thing is somewhat complicated in that we've got three different parts of the system, all that can move relative to one another, and stuff can happen. Work can be done. And we need as a way to sort of catalog what's going on and get our heads screwed on and try to think about it systematically so that we don't get lost in a bewildering morass of complexity. So let's see if we can do that. First of all, I want to point out that objects can change shape, and we've never dealt with that so far in this course. The fact that an object can change shape during the course of some process, and we need to be able to figure out how to deal with that. Internal forces can do work, and they can change their internal potential energy in that way. And also, forces are often very difficult to work out in detail, but oftentimes we're going to discover that energy is an easier concept to work with in these complicated systems. And so when it's possible to do so, it's useful to consider the energy rather than the momentum principle when dealing with these complicated systems. So, what are we going to do? The first thing we're going to do is to divide motion into two categories. And to notice that even in a complicated system, there's sort of an average position of all the stuff in the system. And that average position we're going to call the center of mass. It's kind of a vague definition at this moment, but we'll make it more formal here momentarily. And then the other is that there is also relative motion of the parts of the system about the center of mass. The motion of the center of mass we're going to call translation, and it will have an associated kinetic energy called translational kinetic energy. And the relative motion of the parts of the system about the center of mass, that's going to also have some kinetic energy associated with it, and we're going to call that relative kinetic energy. So let's march ahead. We want to define center of mass more carefully. I do literally mean it's the average position. If we were to divide any object, no matter how complicated, into equal mass pieces, and then compute the average position of all the pieces, that would be the center of mass. So let's take a look at that. If you think about that definition for a little bit, you'll realize that it's equivalent to this formula. And we're going to work on this in class, and I'll actually take you through a process where we have an object divided into equal mass pieces, and then recognize that if there are two pieces that are almost at the same place, we can sort of bundle those together and weigh their position twice. But then that's equivalent to weighing each position in the object by its corresponding mass. And then if you just calculate the straight algebraic or straight arithmetic mean of the positions of all those pieces, you will discover that it's the same as this formula. So anyway, this is the expression we're going to use to compute the position of the center of mass. If you multiply both sides of this expression by the total mass and then take the time derivative, on the left, you get the total mass times the time derivative of the position of the center of mass. And that's equal to the individual masses times the time derivative of each mass's corresponding position. But I want you to look at that for a second. Mass 1 times its velocity plus mass 2 times its velocity plus blah, 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 blah. That's nothing other than the total momentum of the system, the sum of the momenta of all the pieces. But on the left, what I have is the total mass of the system times the rate of change of the center of mass. That's the velocity of the center of mass. So from a momentum point of view, I can replace all the little momenta of all the pieces with simply the total mass times the velocity of the center of mass. And that's essentially what we've been doing all along, is we've been looking at a block that flies through the air. All we've been paying attention to is the center of mass, and we've been calculating its momentum as the velocity of the center of mass times the mass of the whole block. And we've been completely ignoring any rotation or wiggling or anything else that's been going on, and it's worked out okay. So you can see that the total momentum is the sum of the momenta. That's the mass times the velocity of the center of mass. And that also is going to allow us to compute the translational kinetic energy, because we just can calculate 1/2 mv squared, and it's the total mass times the velocity of the center of mass squared. That's if you could think of this as a definition, if you like. This is what we mean by the translational part of the kinetic energy. Now let's do an example. Let's suppose we have a 3 kilogram mass at the location 0, -1 meters, a 1 kilogram mass at 1, 2, and a 2 kilogram mass at 2, 1. And I want to compute the position of the center of mass. So what I do is to simply use the formula 1 kilogram times the position of the 1 kilogram mass plus 2 kilograms times the position of the 2 kilogram mass, 3 kilograms times the position of the 3 kilogram mass divided by the total mass. And before I continue, I ought to point out that if you divide the 2 kilogram mass into 2 1 kilogram masses and the 3 kilogram mass into 3 1 kilogram masses, then you can see that, in fact, what we're computing here is nothing other than the average position, the straight arithmetic mean of the position of all the 1 kilogram masses that make up this system. Notice that the 2, 1, 0 gets counted twice because there are 2 1 kilogram masses there, and the 0, -1, 0 position gets counted 3 times. That's because there are 3 1 kilogram masses there. And you divide by 6 because there are 6 1 kilogram masses altogether. So it's simply the sum divided by the total number of 1 kilogram masses. And it works out. So if you do the calculation, you can see how it turns out. You end up with 0.83, 0.1670. I'll go ahead and draw that on the picture. You can see that that looks like sort of the middle of the picture. That's the average position of all the mass in the system. It's a little bit closer to the 3 kilogram mass than it is to the other guys, and that's just because there's more mass down there. Also, I want to point out that the position of the center of mass in this example is at a location in space where there is actually no mass. So there's no rule that says the center of mass has to be at a place where there's any mass. It's simply the average position of all the mass that there is. Okay, let's talk about energy and momentum. You can work out the momentum principle for the combined system. The result is easily remembered. It's just that the rate of change in momentum of the entire system is equal to the net force on the entire system due to the surroundings. So all the internal forces cancel out because of the reciprocity principle, and the rate of change of the total momentum is simply equal to the net force. Now remember, the total momentum is related to the velocity of the center of mass. So that means that if there's a net force acting on the system, that the velocity of the center of mass is going to change. That's the idea. You can also calculate the gravitational potential energy near the surface of the Earth of all the masses, and it turns out because the center of mass is at the average position of all the mass, that it also has the average height of all the mass, and because gravitational potential energy near the surface of the Earth is just proportional to height, the average potential energy turns out to be equal to the average height times mg. So that's easy enough to do. And finally, the kinetic energy we can separate into the piece that we already identified has having to do with the motion of the center of mass. That's the translational kinetic energy. But there can also be rotational kinetic energy, which has to do with velocities that are perpendicular to a line going from the center of mass to the particle, and vibrational energies which are parallel to the line going from the center of mass to the particle. And basically the vibrational part is the radial motion, and the rotational part is orbital motion, more or less. Okay, what do we mean by a point particle system? A point particle system is sort of what you get when you look at the system from a great distance away. And you're so far away you can't see any of the internal degrees of freedom, and none of the internal motions are visible. You know they're still there, but they're not really visible because the thing is so far away. Let's see what that might look like. So I have a system, I look at it from such a great distance that I don't see all the internal structure. All I see is that I've got a net force acting on the system. And if the thing changes its position, that net force acts on the system as it changes its position of its center of mass and does work. So the idea is, if I sort of smudge out all the internal motions and all I see is the average position of all the stuff, then it looks just like a point particle, and I can treat it like a point particle. I get that the change in the translational kinetic energy is equal to the net force times the displacement of the center of mass. So the idea is, if I don't see any of the internal motions, the only energy there is translational kinetic energy. And so I can compute the change in the translational kinetic energy without worrying about the details of any of the relative motions of the particles relative to one another or any of their changes in internal potential energy. It's simply the net force dotted into the displacement of the center of mass. And of course I can, if the net force happens to be a variable, it's not constant, then I can convert that into an integral. But I would say this is the trickiest part from the whole chapter to become familiar with. After you get the translational part of the change in kinetic energy, you know that if there is any other change in kinetic energy, it's got to be the relative part, the rotational and the vibrational part. So that means that you can use the full system energy principle to compute the rotational and vibrational changes in kinetic energy. So that's the idea. We start with the point particle system, work out the translational change in the change in the translational kinetic energy, and then use the full system energy principle to work out the other ones. And that's the way that works. So let's talk about rotational kinetic energy. We need to develop an idea of rotational inertia. We need to recognize that during rotation, mass that's far from the axis moves a lot more than mass that's nearby the axis. And the axis doesn't have to be the center of mass in all cases, but it's often useful if a particle is just freely moving through space. It turns out the axis would be the center of mass. So generally that's the way we're going to deal with it. And rotational kinetic energy also depends on angular velocity. So the faster something's spinning, the more rotational kinetic energy you expect. And of course we already know that translational kinetic energy depends on the center of mass velocity. So consider here a simple object with 4 masses connected to rods. The thing is spinning around in some way and the masses are moving. But it's a rigid object. So what that means is everything has to be moving with the same angular velocity. So omega is 2 pi over the time it takes for the thing to go around once. And we know that kinetic energy, if we assume that let's say its center of mass is stationary, it's just sitting here spinning, then the kinetic energy is the sum of the kinetic energies of the pieces, but it's all rotational kinetic energy because there's no component of velocity going in and out, and there's no velocity of the center of mass. So the only kinetic energy that remains is the rotational flavor. And I want to point out that the velocity of any one of these masses is just the circumference of the circle, 2 pi r, divided by the time it takes to go around once. But of course we already know that that's nothing other than omega times r. And so we can put that back into the expression for kinetic energy. But notice every single mass has the same omega. So the omegas actually factor out. And what you get is 1/2 of the sum of the mr squareds times omega squared. Notice the similarity of that expression, the sum of the mr squareds, to the center of mass calculation, the sum of the mr's, divided by the sum of the m's. There's a similar thing going on there. The difference is that the r's here are all squared, and so you can never get a negative rotational inertia. This I thing is called the rotational inertia. You can never get a negative value for that. Whereas you could obviously have a negative value for the component of the center of mass. So there's slightly different expressions, but that's how it turns out. The rotational kinetic energy is nothing other than 1/2 times the rotational inertia times omega squared. Notice the similarity with the translational kinetic energy, which is 1/2 times the total mass times the translational velocity of the center of mass squared. Here we have the rotational angular velocity of the system about the center of mass squared. Okay, let's formalize that a little bit. That means that the rotational inertia is the sum of the m times the r squareds, and if I have a continuous distribution of mass, I can turn that into an integral and make that the sum of r squared times dm, where dm is the small chunk of mass. For example, let's try a hollow cylinder. If we have a hollow cylinder, that means all the mass is at a single radius, capital R, and that means R is a constant, because anywhere there's mass, R is always the same. So I can take the R outside of the integral, and then I just get R squared times the integral of dm, which of course is just the sum of the masses of the system, and that's just mr squared. So a hollow cylinder is quite easy. It's just mr squared. Let's go ahead and do a solid cylinder. That's a little bit more complicated. A solid cylinder has mass from r equals 0 all the way out to r equals capital R. And I want to evaluate this rotational inertia integral using the solid cylinder. So let's look at that. First of all, it has a radius capital R, has a thickness little t. Let's say it has a density rho. And what I want to do is to compute this integral. I need to isolate a little chunk of mass that has the same r everywhere from the origin. I know that's a hollow cylinder, so I know that its rotational inertia is dm times r squared. And I need to add those up for all the hollow cylinders that make up the solid cylinder. So a particular chunk, a particular piece of mass has a radius r, a thickness dr, and let's think about what's the total mass of the entire solid cylinder. Well, it's the area of the side of the solid cylinder times the thickness, that's the volume of the solid cylinder, times the density. So the total mass is rho pi r squared t, and the mass of that little piece that I've isolated there is the area, the yellow part of the area of the piece, times the thickness times rho. So it's the volume of the little piece times rho. But what is the area of that that surface, the yellow-colored surface of the hollow cylinder? Well, it's nothing other than the circumference of the circle times the dr, the width of that yellow strip. And if I put that back into the dm, I get the density times the thickness times 2 pi r times dr. And now I can put that back into the original integral, and I can compute the integral. Notice that rho, t, and 2 pi are all constant, so they come out, and I end up with the integral of little r cubed dr from the origin all the way out to big R. Of course, that's an easy integral to do. It's just big R to the 4th over 4. I can simplify, and I get that it's pi rho t r to the 4th over 2. Now, the thing is, I don't necessarily want to have to find the density and the thickness of every cylinder, but remember, I already know the total mass of the cylinder is rho times pi times capital R squared times t. And notice I've got a rho times pi times capital R to the 4th times t. So I could factor out the mass of the cylinder, and it turns out then I get the simple expression 1/2 times the mass of the entire cylinder times r squared. So remember what we got for the hollow cylinder. It was just mr squared. For a solid cylinder, it's 1/2 mr squared. And you can, of course, reproduce this calculation for a variety of different shapes. It's great fun. If you're bored sometime, you can go and calculate the rotational inertia of all these different shapes. But I've gone ahead and made a little tabular representation here for you in case you're curious. I think there's also a table like this probably in the book somewhere. If not, you can Google it at any time. These are well-known results that people have worked out a long time ago. Anyway, let's take a quick review of some of the variables we've been dealing with, because I think this is a good time in the course to stop for a second and sort of reflect on all the different variables we've dealt with. First of all, there's the kinematic variables of position, velocity, and acceleration that are related to each other by time derivatives. The velocity is the time derivative of the position, the acceleration is the time derivative of the velocity. We have this concept called mass, which has to do with how much stuff there is. And we have this idea of momentum. Of course, this is the non-relativistic momentum, only for speeds much less than the speed of light. But we could generalize that. We've got the idea of force, which has to do with the rate of change of the momentum of a system. And we've got the idea of kinetic energy. In this case, it's the translational part of the kinetic energy. It's 1/2 the mass of the system times the velocity of the center of mass squared. But I just put 1/2 mv squared to sort of remind us of the structure of the thing. What I want to point out is we've added a rotational form of kinetic energy, but we're going to be dealing with problems that involve all kinds of rotation, and I just wanted to take a minute to discuss the relationship here. When we're describing a rotation, we need something like position for rotation, and the position turns out to be the angle. So if you rotate a thing a certain amount, that is represented as an angle. But then the angle can change in time, so we have an angular velocity, the rate of change of the angle. And the angular velocity can change in time, so we have an angular acceleration. And you may remember that there were some algebraic solutions to the momentum principle, basically, that were correct as long as the force was constant. We're going to find out, and as long as the acceleration was constant, and we're going to find out that there's similar equations for the case when angular acceleration is constant. So we'll take a look at that in class. Now, for mass, there is a sort of analogous quantity. It's called the rotational inertia. So rotational inertia plays the same role that mass plays in translational motion, but it does it in rotational motion. And we're going to find out soon that there is an angular momentum associated with rotation. Now there are two flavors of angular momentum. There's orbital and spin, and this turns out to be the spin flavor. There's also another type. This I omega is the spin angular momentum. We're going to find out that there's another one that's related to the angular momentum an object has when its center of mass orbits another object, or orbits the origin. Their idea of force has an analog. It's called torque. Notice that the force turned out to be the rate of change of the momentum. The torque is the rate of change of the angular momentum. And I like to bring up a cause and effect nature here. The net force causes a rate of change of momentum. The net torque causes a rate of change of angular momentum. Torques are brought about by forces, but you have to calculate a torque. So we'll see how to do that soon enough. And finally, there's the rotational kinetic energy, 1/2 I omega squared. What I want to point out here is that without even knowing what all these goofy letters mean, we can already see a pattern in the relationships between them. So if you know a relationship that exists between the translational quantities, position, velocity, acceleration, momentum, force, kinetic energy, you already know the relationship that exists between the rotational quantities, because it's simply a question of substituting the right letters and putting them into the relationship. So I only want to bring up this table now because it it's good to recognize as early as possible that there are these analogies that exist between translational motion and rotational motion, and you can take advantage of your knowledge of the translational motion in order to get insight into the rotational motion. Okay, so we're going to do some examples. At this point, I'm only going to work out one example, but I'm going to give you an example to work out and bring to class on Friday. And in order to do it, I want you to go find the Rolling Motion podcast. I put a URL on ACE so you can track it down. For those of you watching on YouTube, you can go to the playlist and find the Rolling Motion podcast and look at that. What we're going to do right now is an example of a person crouching and jumping, and that's an example of a body changing shape. The strategy is to work out the point particle system first, and once we know the change in the translational kinetic energy, we can use the real system to find out the change in the internal energy of the system. So that's the idea. We have a 1.73 meter tall vertical jumper. He crouches down, leaves the ground with the speed v0, assuming they can lower their center of mass by 25% of their height, and that they can exert a normal force 3 times their weight. In other words, they can push down on the ground with a force 3 times their weight. What speed can they achieve? How high is the center of mass after the jump? Is their center of mass after the jump? Let's look at that. So we're going to work out the point particle system first. They're going to crouch down, and then they're going to jump. So I have two images here. One is before they start moving as they're crouched down, and the second image is just as they're about to leave the floor, so they're completely uncrouched and they're moving with some speed upward. They're moving with some velocity upward, but the speed is v0. So we can use the point particle system result that the change in the translational kinetic energy is equal to the net force on the point particle system times the displacement of the center of mass. Now, the point particle system, by definition, is a system consisting only of a point particle, which has the mass of the entire system. So we're going to scrunch this person into a point that's located at their center of mass. And we're going to notice that the net force acting on them is the normal force plus the weight, and it gets displaced by a distance a quarter of their height, right? Because their center of mass is going from the point it was when they were crouched down, a quarter of their height below their original center of mass location, and it's going to go back up to the original center of mass location at the moment they leave the ground. And we can work that out. Now, the change in the translational kinetic energy, of course, they start at rest, so the change in the translational kinetic energy is 1/2 mv0 squared. The weight acts down, the normal force acts up, and so the net force acting on them is going to be, actually the normal force was 3 times their weight, so the net force is going to be 2 times their weight times their displacement. If you put in h for their original height and calculate all this, you end up with a speed that's about 4.12 meters per second, given their initial height. So that's the kind of thing you can get with the point particle system. Next, we can analyze the real system. So we forget about the point particle system, but we remember that we worked out the speed and we worked out the work done, and so on. The change in the energy of the system, the real system now, is equal to the work done on the system by the surroundings. Now we have to decide what our real system is going to include. I've chosen to include the jumper, include the earth, but not anything else. So let's see how that works. Because we've got the jumper included, we've got his change in translational kinetic energy. We've also got the earth included, so we get a change in the interaction potential energy between the jumper and the earth. And I'm going to say that there's a change in the internal energy of the jumper, but there's no work done on the jumper by the surroundings, because the contact point between the earth and his feet does not move, so the earth actually isn't doing any work on the jumper. So those guys have to add up to 0. Now, if you put in the known change in height of the jumper as it goes from A to B, and you put in the known now, the known change in translational kinetic energy, we can actually calculate the change in internal energy. The change in internal energy turns out to be minus 3/4 of mgh. And that means that's the energy. So if there were he ate some Wheaties this morning and that jump required some energy on his part, this would be the amount of energy that was extracted from his body chemistry or physiology or whatever. His muscles is the idea. Okay. Now, what about how high he jumps? How do I handle the jump? So the idea here is we create a new point. We'll call it point C. Right now we've been dealing with the point when he's crouched and the point when he just got off the floor. Now we're going to create a new point called C when he reaches his maximum height. And at that moment his velocity goes to 0 and he reaches a delta y that we want to find out. We want to know what is the delta y. How high does he go? So let's work it out. Again, the change in the energy is the work done on the system by the surroundings, but we know the floor does no work, and we're including the Earth in the system, so we don't include that in the surroundings. We know the translational kinetic energy is 0 at the top and 0 at the bottom, so there's no change in translational kinetic energy. So the basic idea is the change in the gravitational potential energy must be equal to the change in the internal energy. But we already worked out the change in the internal energy. That happened between points A and B, and so we can simply put that in, and we know that that is the only energy available to raise the potential energy. So we can solve then for delta YAC, and we find out that it's 3/4 of the height. And that's pretty much the end of the story. That's how it works. So I hope that was helpful, guys, and we'll see you next time.